Okay. Hello? Can anyone... You hear me, right? Okay. So I will talk about Linux containers, but before I start, I want to tell you why I'm talking about containers. I am starting a new company called GetCloudr, and the problem is that there are a lot of issues with containers, and actually the community wants to solve a greater container problem, while I simply want to have isolation from other containers on the same machine. So I decided to attack a smaller problem instead of the bigger problem that the kernel is trying to solve. So first, before we continue with the issues, there is a differentiation in containers. A container may be a contained application that is working without root access, or a container can be a whole operating system that is contained in different environments. Containers are not virtual machines, but I believe they should be. So Docker is application containment, while Linux containers, LXC, is a project that tries to contain a whole operating system to give you a virtual machine experience on the same machine without actually running multiple kernels. So yes, LXC is not a virtual machine. As I said, it should be, and the problem is that at the moment there are a lot of applications that, if they are contained, they would see everything about your machine if you mount proc in that container. And these containers usually are limited to some extent, and also there are normal users on this machine. A lot of processes really actually need a lot of security context to actually work. So they would need to bind to ports under 1024. They would need to access sockets and files that are root owned. And this is a problem because you don't have a root in your container. So first of all, I decided to make a container that actually works a lot like virtual machine. So the first thing is that every one of you is used to looking at proc CPU info and seeing the processors that he has access to. On your laptop, that would be all of your processors, all of your cores. But on machine with, for example, 80 cores, and you limited this container to only 2 cores, it shouldn't be possible for this container to see all of your processors. It should see only the 2 processors that it needs. And why this is important? Because a lot of scripts and software actually rely on the number of processors for deciding how many threads they should start. For example, there are scripts that run make and make with -j, and they decide how many GCCs it will start based on the number of processors that you have in your CPU info. And if you start 80 simultaneous GCCs on a container that has only 2 cores, obviously this will be a very big performance problem, and instead of building your software faster, it will slow down tremendously, like at least 20 times slower build. So you have another issue like web servers or web proxies that decide the number of threads, the default number of threads, based on the number of cores they see on your CPU info. So that's a problem, obviously. So yesterday I showed you how I first approached that problem. Now, a few months later, I decided to actually change that. So the problem is that you have to limit the information there to only what you have provided to this container. CPU info is only one part of it. You have information in proc interrupts, shed stat. Shed stat is very important because top is actually looking at shed stat. If you get more CPUs there, you see more CPUs there, you actually don't see only your CPU usage. So it's a problem. Soft IRQs, stat, timer list, zone info, all of these files expose the whole machine instead of what you have limited your container. IRQs also expose information to the container, and most of the time IRQs are useless to the container, but for some software, IRQs are very important. And if you have given access to these IRQs to this container shouldn't see all the rest of the IRQs on the machine. It is possible that you can dedicate an IRQ to a container. It's hard, but it's possible. Memory. Memory is hard part. Everyone is using proc meminfo for information. Everyone that uses the free command actually sees information from proc meminfo. And if the memory information there isn't the information that your container is the information for the whole machine instead of the information that is supposed to be only for your container, your software again does the wrong thing. So if the machine has half a terabyte of RAM, your software may decide that it actually can have half a terabyte of RAM, but your container may be limited to 4 gigabytes of RAM. So what happens? You configure your MySQL, for example, for half a terabyte of RAM, right? And you actually get something completely different. The performance is awful because most of the time your MySQL is either crashing or swapping. So it's not working. It shouldn't be like this. So what we did was we changed the meminfo so it gives you the information out of your limits instead of what the system sees. Other things are like if you run one kernel, you have one kernel administrator on this machine, and that is the true root of this machine, the one that has access to the physical hardware to this machine. So every container shouldn't be able to load modules. It's obviously a security problem. If you allow your containers to load modules, they actually control your kernel. You don't know what they can do with that. Another problem was, and this was fun when we researched it for the first time, there is a file in proc criu trigger, and if you write B to it, and it will reboot your machine. So if you have this file in the containers, and you don't change the kernel, you actually get, every container can now reboot your host machine.
Can I interrupt?
Yep.
Does this also apply to unprivileged containers?
No, this applies only for root containers. Unprivileged containers don't have this problem because unprivileged containers are single application containers. For example, Docker doesn't have this problem at all. But if you want to switch from virtual machine to a container, this is a very big problem because you have to give root access as you have given root access to a virtual machine. And before you ask, please, there is a very real need to switch from virtual machines to containers. What we did was a very simple test with WordPress installation with Apache and MySQL on a virtual machine, and we installed 40 virtual machines on one big physical machine, and we did a siege test on these machines, on these virtual machines, then removed the virtual machines with the same storage. We created containers and did the same siege tests, and we got around 20–22% better performance out of containers without the virtual machines. And also we saw I think it was around 30% better memory usage, and by better I mean less memory usage and less memory contention for different parts of the memory.
Just want to say that the new unprivileged LXC containers actually support that you have root in the LXC container, but you run it as a user.
I'm talking exactly about that. And all of these problems that I mentioned now are for these exact situations where you have a fake root inside of the containers. You map, for example, user ID 500 from your host machine to user ID 0 in the container. And now user ID 0 is a privileged user within this container. And as a root user, which is the check in the kernel, he can trigger sysrq trigger. And there are a lot of other things, and I have 2 or 3 slides for security only. So I know that last year you had an LXC talk here. So I focus more on the problems that I solved, or at least started discussions on the kernel mailing list about these problems and their solutions. Now, the file system directory usually shows how, which block devices you have connected to this machine. The problem is that if you have a block device and you have a root, even fake root, inside the container, this root have access to these devices, so he can actually format the device or create a file system there that will overwrite your file system or even mount it. That's a problem. So you have to either remove these devices that he couldn't see, but when you remove the information, this doesn't mean that you remove the access to these devices. So for this, you actually have to go to the devices C group, but I'll talk about this later. The SCSI directory also leaks block device information. The sys directory allows writes to root. So from there, you can change a lot of things on the machine, like shared memory usage, buffers for TCP, and stuff like this. And you don't want a container to actually change these settings for your host machine, right? You don't want to, the container to be able to change anything for everyone on the machine. The root on this container should be able to change things only for his container. Now, the other thing, uptime. Uptime is, you get uptime from the kernel. So when you use the uptime command or cut the uptime from proc, you actually see the uptime of the host machine. If you reboot your container, you still see the uptime of the host machine, which is completely stupid for me. A lot of people use the uptime for statistics and some stupid things inside their containers or virtual machines. You need to know when your machine actually booted, when your operating system started. So I also changed that. There, the problem was that you had to find the first process that actually started and get its start time and get the uptime, and remove the start time from the uptime, and you get the actual uptime for this virtual container. Now, security. The kernel for a lot of years now have capabilities. Most of the software doesn't use capabilities, but if you are planning to use containers for to have a root inside these containers, you need to be aware of capabilities. I advise you to read the man page capabilities. It's called capabilities, and read everything. It's not very long, but read it and understand them, and understand why you should remove all of these. I will not stop to each of these, but I'll give you an example. Capsys boot gives you access to the kernel, to a syscall in the kernel, which when called, you will reboot the host machine. It's the same like the sysrq trigger, but it is a syscall within the kernel. You have similar thing with sys-raw.io. You get access to the block devices, and you can create file systems, you can change partitions and stuff like this. Now, the next thing. I don't know if you know, but K-core and VM core actually expose your memory. So if you get, if you mount proc within a container, proc is one proc file system. So if you have K-core for the host machine, you have the same K-core for the container. And if the container can read this file, he actually can read the memory of the whole machine, all processes there. And if you have never tried that, cut your K-core and try to see strings from your web browser, from your webmail, from your mail client, and stuff like this. You will see clear text there because you're actually reading the memory. So if it is like stored as a string in memory, you read a string. So it's a big, big issue. Usually only root has access to these files. But as I said, you have root inside the container, right? So he has access to these files. Now you have to either remove them or patch the kernel so the container doesn't see that. The same goes for KO sims. And in order to achieve all of these things, I decided, okay, I'll introduce a new capability. This capability will be given from me only to processes that are on the host machine, and every process that becomes a container, because it is becoming a container, should drop this capability. And without this capability, he would not have access to K-core, he would not have access to VM core, and the next part, most of the patches that I have done depend on this capability. Why this is not accepted? I already tried to commit this to the kernel. Why this was not accepted? It's simple. The kernel guys want to have hierarchical namespaces and control groups. This means that you have one parent, then you have a child, and this child can have another child, and so on. This means that if you drop the LXC capability, now you would not be able to have, your child should not be able to create a new container, new namespace, new control group. In my case, this was the best solution because I didn't want to have hierarchical structures. As far as I understand it, it takes a lot of time to walk all of these hierarchical structures in a very big environments in which I work. So it's a big performance problem for me. So since it is a performance problem, I'm not allowing it, and I'm creating a flat structure with one root and a layer of containers that doesn't have this capability and the rest of the things. There's another problem. When you create a container that has root access, he can create a lot of processes there. And you don't have the next point, R limit number of processes. I assume that most of you know what U limit is. You don't have U limit for the whole container. You have limits per user. But in this container, you may have 1,000 users. And which user is actually responsible for creating many processors, you don't care. If this container creates a fork bomb, it will be a fork bomb for the host machine. So we were speaking with some of the kernel developers about that, and this should be fixed with the KMM control group, and you should set the number of processes multiplied by 8, then multiplied by the structure size for the process, and by now you should understand that this is not very easy for system administrators or even for you. So there was one guy that developed a new control group mechanism that is called task limit. And it's not accepted mainline, same as my patches, but it works. You simply patch your kernel, he supports it, I support that also. With this, you can actually limit the number of processes within a control group. And you don't need to know the structure size, you don't need to know this magic number 8, and it's a lot easier for you. So this is the number of processes within a container. You have to limit them because fork bombs are very real threat. And then you have this strange problem that I'm currently fighting. It's the R limit number of processes. Now, you have this strange situation where you create a container and you have this ID mapping for the Linux containers where you can map a certain user ID, as I said, 500, to another user ID in the container, which would be 0. And this means that if I start all of my containers with the same mapping, this means that user 500 now has all the processes that were started with user ID 0 within the containers from all containers. And the argument number of processes is accounted by the user ID and at the host machine 500 instead of the user ID 0 within the container. So if one container starts 100 processes, another container sets a number of process limit to 100, the second container wouldn't be able to start a process with user ID 0. And the container wouldn't know why, because only the host machine knows that it accounted the 100% of processes from another container, not the second one. This is a very strange problem, and you have, strange as it sounds, you have the same issue with signaling, because signals are also accounted by user ID, and it's strange, but there is a limit to that. So both of these limits have to be made to work per container. Usually when you go to the kernel guys, they would say, oh, you shouldn't ever do this. You should map different user IDs for different user IDs in the containers, which means one container would start with user ID 500 and you map from 500, for example, to 1000 for the first container. And this would be 0 to 500 in the container. Then from 1000 you should go to 1500 for the second container. This is a problem because, for example, if you have block storage like LVM, and you pre-provision your containers with a snapshot of this block storage, the file system there has certain user IDs. And these user IDs are actually, they don't change when you do a snapshot, right? So when you mounted the new snapshot, you get the same file system. And now, for example, you have 4 or 5 gigabytes of storage for your basic operating system. Because you change the user ID mapping, you now have to change the ownership of all of your files within this new provisioned file system. And since you used snapshots to be fast, now you get a lot of I/O only to chown your files, which is stupid because you already lost all of the speed that you got from the snapshots. And you have similar issues with NFS, with cluster file systems. So it's a problem. It's a big problem. And you cannot, in a big environment, easily do a pre-reservation of user IDs. So it becomes a very big issue for the host machine to have different user ID mappings. As I said, I decided to make the namespaces infrastructure and the control groups infrastructure artificially flat. It is still hierarchical in the kernel. I didn't change anything about that. Simply, I am using it as a single root with one line of multiple containers. And there was another big thread that I started a month ago on the kernel mailing list. I assume that most of you know what change attribute is, ch-attribute. And this command is commonly used by system administrators to protect log files or to protect sensitive files that shouldn't be removed even by root. And this is the immutable flag that usually they use. But it happens that the check for the capability cap Linux immutable is done against the host machine instead of the container. So even if you may have the capability inside the container, since you are a normal user outside of the container and there you don't have the capability, the file system code in the kernel doesn't allow you to do to create immutable files. It's stupid. Why it's done this way? We started talking about this, and again, differences in approaches came that maybe this will be fixed in future releases, maybe in a year. But for now, no one actually agrees to a single solution. And the problem there is that if you share a file system with your container, you're fucked. Because the files that are, the file system is shared between different roots, and the root have access to recreate different files. Even, for example, there is an attack on hard links. I can create a hard link that looks exactly like it was created from the host machine, but it points to a file that is inside the container that I control. And a lot of other different attacks against a single file system. So in my case, since I would never share a file system with a container, I decided that I'll simply introduce the check. I would change the check in the kernel from capable cap Linux immutable to NS-capable cap Linux immutable, which means namespace capable. And it was a very simple change, only 3 characters, and it worked. I had to change it for all the file system that I plan to use. So when I spoke with some of the LXC guys, they agreed that this would work for my case, but this wouldn't work for everyone. For the guys that want to share a file system, this is a problem, because now a root inside the container can create immutable files for the root outside of the container, or even worse, for containers, for other containers on the same file system. So sharing a file system with containers, no, no, no. Now, umount. You may want to unmount a file system from your container. Yeah, you may want to do that, but you shouldn't be able to do that because the kernel says that only the true root on the machine has access to mount and umount. So now, if you have mounted, for example, TMPFS somewhere, you cannot unmount it from within the namespaces. So the issue is that when you create a container, you have a mount namespace, and I'll speak about mount namespace in a minute. But this mount namespace actually has a copy of your mounts, of the host machine mounts. And most of the time you want to remove some of the mounts that you have for the host machine. And you have to be able to do that inside the container. And if the container sees only these mounts, it cannot actually unmount anything on the host machine. It took us a little while to actually figure out how to make it secure in the kernel, because umount, the command umount, is not the actual kernel code for umounting. And you can actually create a very small binary in C that can try to unmount the root file system of the host machine. It took us some time, but we figured it out, and you can now actually unmount only file systems that were mounted for this container and that are actually seen inside this container. Because after you create a mount namespace, most of the mounts are not visible for the container itself. Now, devpts, how many of you know what devpts is? No one knows? Okay, so I'll have to explain that. devpts is a file system, pseudo file system like proc, but it is only for terminals. Your terminals that you create with your G terminal, with SSH and stuff like this. But if you have only one file system for your host machine and mount it for all of your containers, unfortunately, the root of each container own all of these devices. So he can actually sniff on your SSH without actually SSHing to your container, because he can actually read the key presses, the characters that you sent via SSH to this device, and actually send more characters to the same device. So this is a problem, obviously. You don't want your containers to share PTS devices. So in order not to share that, the kernel guys have developed an option in the dev PTS which is called new instance. So you can create new instances, whoops, new instances to for each container, and each new instance have different major minor numbers, so it means it is completely different device, and each container now has its own devices. But if you allow mounting of dev PTS in the container, the root inside this container can decide to mount dev PTS without the new instance option, and he will actually mount the host dev PTS inside the container. And now again, he has access to the host terminals. So in order to solve this, we simply said, okay, if you have LXC, cap LXC admin, you can mount the host dev PTS. If you don't have it, you can mount dev PTS only with the new instance option. It fixed our problem altogether. Okay, so there are some privilege controls that you can trigger from user space to the kernel. One of them is PRCTL set MM, and there are others, but I decided to use only one, for example, that shouldn't be allowed for the container. Like you shouldn't change this shared memory limit for the host machine. You can change it for your namespace, but you shouldn't be able to change it for your host machine. And this case actually is very stupid, because this syscontrol was never patched when they introduced namespaces to support namespaces. So instead of trying to see if you are in namespace and change the values inside the namespace, it actually changes the host parameters. So the container stays with the same stupid limit. They cannot change their limit, even though they have access to it. So we fixed that. And then the other thing, pivot root. Pivot root is actually the mechanism to create a container. You you mount your block device, and then you change the directory to the / of this block device, and then you change routes by simply moving your old root in another directory, and now this root that you have is the only root for all the processes from now on. And now you can simply unmount the whole the old root, and the container now doesn't see the rest of the file system and everything that was mounted there. The problem there was that it works pretty nice with LXC, but we also do live migrations. We do checkpoint restore with the criu software. And when you are restoring a container from one machine to another, when you are restoring the actual container, you are already in the container. So you don't have access to pivot root. So we patched that again. If the process that is actually doing pivot root has cap LXC admin, it can do that. The other thing is setns. Setns and unshare also. Both of these functions are syscalls. They are created so you can create a very simple software and change your namespace. And for example, change your network namespace or mount namespace, and now you can actually see other file system or file systems or other network devices. And you shouldn't be able to change namespace from within a container. This is our assumption. But this breaks the hierarchical structure of namespaces. If I stop on the first child, then this child cannot set namespace, change the namespaces to the other childs. And I implemented also a solution that wouldn't break the hierarchical structure, but unfortunately, its performance is bad. Obviously, because you have to go through all the namespaces and check if it has access within those namespaces. And if the parent also had access to that. So some of the solutions are very crappy, and doesn't work for everyone, but they would work for a hosting environment or for your office environment where you want to have more containers with root access instead of hierarchical structure that I don't know who will actually use. The other thing is hardened proc file system. I'm using these patches for around 10 years now. Proc gives away a lot of information, and if you don't know, most of the malware that is running on Linux actually abuses this information so it can grow its privileges, do more nasty stuff, hide itself in different parts on your file system in different libraries. So exposing this information to different users within your machine, and here I don't care if it is the host machine or the container, one user should see only the information from proc that is relevant for him. So he cannot go inside another process and get information from this process, from the kernel for this process. This shouldn't be happening. But by default, the kernel allows that. And this is something that, as I said, for 10 years I'm changing in all of my kernels. So a single user cannot actually see the processes from another user if it is not root. Another thing that I want to point to is GR security. Most of the people that I spoke with about containers say that you cannot run containers without SE Linux. I do agree to some extent, but you can replace SE Linux with GR security. And the problem is that SE Linux actually doesn't do anything to protect your memory from memory attacks. It don't protect your processes inside the kernel from attacking other processes inside the kernel. GR security have a lot of additional preventive measures, and even if you don't use its Mac architecture, you still should use its memory protections. So the problem is that Spender usually releases one GR security patch for the latest kernel and nothing else. So I did a very small cron job that downloads every new patch for the GR security and uploads it to this site so we can have a history, because, for example, I'm not working always with the latest kernel. Sometimes I'm working with the older or with an older kernel, and I cannot see the GR security patch for this older kernel. And GR security patches are immense. They're like 20 or more thousand lines. And they also include assembly, strange C, and fixes that you wouldn't understand even if you understand the languages. So in my case, it was easier to simply have all the patches from Spender sorted on one place. If you want, it's publicly available. You can download it download them from there. Now, functional changes that we did. I started with kernel 3.10 for my changes. Now I'm working with 3.12. And since I'm not working with the latest kernels, there are changes for the shared memory, semaphores, and message queues inside the kernel. The limits are actually hard-coded in the kernel. Every time you initialize a container, you get this hard-coded value. And even if you change the value on the host machine and create a new container, you still get the hard-coded value. And unfortunately, the root inside the container doesn't have the ability to change these limits. And what we did was very simple. We changed the code that initializes IPC namespaces, and instead of using the hard-coded values, we simply copy the current values of the root namespace to the new namespaces that are created. For the new kernels, this shouldn't be a problem because all of these are set to long, so it should be enough and it cannot be more. So that's the reason why they didn't accept these patches, because they are for older kernels. And they said, okay, don't worry, for the new kernels, you don't need to do that at all. Again, it is hard-coded value for all the namespaces. No one copies anything, but at least you don't need to increase it anymore. One strange thing that we noticed was we changed kernel versions a lot. Obviously, from 3.10 to 3.12.21 right now, we changed every time the kernel. And inside the container, you have tools like IP tables that really need to know your kernel version, and based on the kernel version, go and find the dependencies for the modules, and then decide if you have loaded the modules or not. Or which modules the user space to have to load. So this is a problem. If you change kernel version on the host machine, you then should go to each container and create the new directory and push the new modules deb file in each container. Usability problem and a major problem at all. So we decided that we will not fix that. We will not do a user space fix for that. Instead, if you are inside a container, you always see a hard-coded version for the kernel that I decided what was it. And I can change it from the host machine. It's stupid. No one will ever accept that, and they shouldn't. I agree. But it works. It solved my problem. Another issue was that containers are actually non-recognizable for any software that differentiates between a physical machine and a virtual machine. And this is a licensing issue. If you want to install a software that is a lot cheaper for virtual machine inside a container, you cannot, because the software cannot recognize this as a real container. So what we did was we looked through the Linux vServer code. And the Linux vServer code adds 2 lines in proc status for your process. And these 2 lines give you some IDs. So since we are not Linux vServer, and we don't intend to be, because the containers are something else, we simply added these 2 lines with hard-coded values. And now the containers, the software inside the containers may recognize us as Linux vServer. And since containers and Linux vServer actually don't, they're not so different from each other, they can be considered as the same virtualization layer. So for licensing purposes, this worked very well. Now we have IP tables XT owner. I don't know if any of you is using that, but when you want to limit the outbound connections for a certain user, match owner is perfect, perfect for the case. But with IP tables, even though you have a separate network namespace, which you can create your own name, IP tables, rules, and IP sets, and so on, you cannot actually use the XT owner because it is specifically forbids that. In the code, it forbids that. So I had a patch proposal for this one. My patch worked. It wasn't the best solution. It worked. Then Biderman said that it's not the best solution. I'll write another one. He wrote another one. His even didn't compile. After we fixed it, it didn't work inside the container. We still are poking around this to fix it in the mainline, but most probably for 3.16 or 3.17, we will have it fixed and working there. Another strange thing is that traffic control doesn't work inside the container. You have network namespace separate for this container. IP router works, IP tables works, EB tables works, but traffic control doesn't. So you cannot do shaping inside your container. You don't have access to traffic controls. It's strange, but in 2012, there was a guy that actually said that this is a problem and this is how you can fix it, and there is a patch on the kernel mailing list that works actually, but it's not accepted in the mainline. It's perfect for me because it actually works it's well documented, and it got through the scrutiny of the kernel people, but simply it did some of the things differently than the kernel people wanted. But since I'm building a custom kernel, I don't mind. I got the same code, it compiled, it worked, we tested it, perfect. It worked extremely good for us. So we started with live testing. We started with 3.12.0 kernel. And we started with 3 machines. We put new customers on these machines, each in another separate container. And after the second day, these machines, all of them started to reboot, like 2 hours working, 5 minutes reboot. 2 hours working, 5 minutes reboot. And we were baffled, what the hell happened? Since we were also using some proprietary patches from another company, we first thought that this is a problem, this is their problem. But actually it was the Ohm killer that broke the system every time. So we looked around for a solution. We patched our kernels by ourselves. Then we found that in 3.15, which is 3 versions from ours, they fixed it. And I started backporting these patches for 3.12. Then suddenly I realized that SUSE are using the 3.12 branch, and they already have backported these patches. So I used those patches from SUSE to fix our problem from upstream. And I realized that only after talking with Jiri, which is he is responsible for their kernel development, and he mentioned that I don't need to repeat his work. So working with the community is really, really important whenever you're working on these big projects. Then there is another problem with performance for the memory manager. If you're working with these big machines, as I said, half a terabyte of RAM and a lot of containers on this thing, OhmKiller has this very neat mechanism to search for the right task that is using the most memory to kill. But this takes a lot of time and also blocks all processors. So if one container blocks for OhmKill, all of the rest of the containers are blocked because of this OhmKill. And there was a discussion in the beginning of 2013 about this on the kernel mailing list. No one did anything about that, except one guy that posted the patch. No one accepted the patch, but it works. Again, solutions that work for niche cases like mine doesn't work for everyone. But if you post your patches on the mailing list, like these guys, like my patches there, everyone can find them, and they can build their own custom kernel as they want. And the rest, ProQuote average. That's a very, very tricky one, because you have the load on your system on the host machine. And this load is calculated by a very strange long formula. And it takes a lot of hours to understand that formula. Actually, I spent like 2 days to understand it and to actually manage to make something useful out of this formula and how it is calculated. And the problem is that in ProQuote average, you see the load for now, the load for the 15 minutes ago, and then you see how many threads are currently working in the processors, how many processes you have running at the moment, and the last bit. So there are quite a few changes that you have to do there. Last PID, current number of processes, and current running threads is pretty easy to fix. It takes around 2 to 3 hours to actually fix it. But the calculation of load now becomes a very big problem, because you have one number for the whole machine, and you have the same number for all the containers. And you have to find a solution for this. And firstly, we decided, okay, we'll do it inside the kernel. But then I saw that if we go this way, the problem is that we have to change the scheduler, the process scheduler of the kernel. And this is very, very delicate part of the kernel, which most people shouldn't change. And we decided not to, because it works well and we don't want to fuck it up. So we decided to create a user space system for this. Since you have accounting for I/O, memory, and CPU, and these are the basic three things that are used in the formula for the world average, we collect the information, and this data is updated every 5 seconds. We get this information every 5 seconds for each container, which is only from the control groups. And we calculate percentage of world from the world value that you have on the host machine for each container. And then we actually put it at the world average file on each container. And the world average file is a normal text file that is actually bind mounted to the proc file system for each container. It worked very well, and actually it worked better than trying to solve this issue inside the kernel. Trying to solve the issue inside in the kernel will take us around a week or two to fix, while solving it in user space took us a day or two, maybe with the testing. So these are the problems that we faced with containers with root access inside of them. Now, please, how many of you know all about this, about this slide? Okay, how many minutes do you have? How much time do you have?
Minus 30.
Really?
We are running all the time.
Okay, then. Okay, I want to tell you about criu, nothing else. Checkpoint restore in user space. This is a tool developed by the Parallels guys, the OpenVZ guys. The problem is that it was made to work for their containers. Now they try to make it work for everything, and it's a bit problematic. We patched a few things. We worked with them to fix a few issues, and we had to develop another separate software in addition to criu to actually migrate a container from one machine to another machine within under 1 second. So the issue here is that you have to stop all of the processes inside of this container here, stop them for a small amount of time, do a memory checkpoint and memory snapshot, dump all of the memory to disk, and then on the other machine, restore the memory and the state of the processes, and then simply start the process. You can do this in under 1 second only if you have shared storage between these machines. Either if you don't have, actually criu can support copy and write, and you can copy the files from one machine to another, but obviously it will take you more than 1 second. It's good because you can now actually dump a whole group of processes from one machine, stop it for a week or so, and then restore it on the same machine or another machine. You don't care. The very great thing about this is that, for example, if you have one machine that is running certain containers for build, that is not important at the moment, and you also have another container that really needs the resources for rebuilding something else or working with another software, you can simply stop this container, the whole container, save it to file, and then release all of the resources, continue with your work, and then restore it once you have more resources again. Or also, you can do, if you need to change the memory, for example, from one machine, you can simply save the container, move it to another machine, and restore it there as it is, never stopped. Okay, so since I don't have more time, thank you.
It's now awesome.
Come on, just tell us a few sentences about snapshots and how are you using it, the file system, the slide before criu.
Okay, I'll tell you what we use. It's proprietary software, but it's another Bulgarian company that did software-defined storage. So we have a cluster of for example, 10 machines, and we write in hybrid between SATA drives and SSD drives, and we always read from the SSD drives. Actually, our storage is faster than SSD at the moment. And these guys offer us snapshotting. But since you're not using these guys, you can do the same thing with LVM. And what you can do is create a volume that you install your operating system. And after that, you use this as a template. Don't change that anymore. Create a snapshot of this volume and create this snapshot can be read-write snapshot. So you can create this read-write snapshot and you have new containers out of the same file system actually. And you can have as many as you want snapshots. Okay, it's not as many as you want, but it's a high limit, okay?
You will get right amplification.
At certain point you have to... No, at certain point you have to detach the snapshot because you have more changes in the snapshot than on the it takes more space on your hard drive to save all the changes between this snapshot and the original volume. So usually what we do is we create a snapshot and immediately detach it from its origin, so it actually takes the whole space. It's not only a snapshot. But it's very useful because, for example, we have a script that mounts all the volumes and does apt-get upgrade or yum upgrade inside this volume, and then rearranges the other volumes that are made, the other snapshots that are made from the first origin.
Kratko, molim.
Do you think that kernel developers have decided of what actually LXC containers should be? What should be the scope of LXC? Should it be almost a virtual machine, or is it in flux? How?
You have to differentiate the two things. The kernel guys are completely different people from the LXC guys. LXC guys really think that LXC should provide a virtual machine layer, virtual machine-like experience for the distributions that run inside LXC. While the kernel guys, they simply look at the kernel architecture of the software, and the kernel architecture is hierarchical structure all the way down. And there were some talks, and I mean like 120 mails on the kernel mailing list about should they continue with the hierarchical structure because they know that it's slow, it's cumbersome, and it doesn't work very well, but they still continue to do so. So I don't know, maybe in future this will change, or at least will be limited, the hierarchy will be limited. So the LXC guys really work with the kernel developers to provide this isolation that would look exactly like virtual machine. How long it will take to convince them, I don't know. I actually try to approach them, and also said that I'm trying to go to the Linux Plumbers conference. They have a containers mini conference, and I applied to go there and speak about this because obviously I'm one of the wildest mouth on the mailing list about this, and maybe I may convince someone that this is a good thing to do.
Thank you very much.
Thank you.